Welcome to the Material Minds podcast, a place where we talk to the people exploring new materials for a better world. Today, we talk with Roland Bennewitz, head of the Interactive Surfaces Research Department here at INM. We play a fun little game to get to know him, talk about the feel of gift wrap paper, how to make nanodiamonds with an atomic force microscope, his favorite material that he brought along with him, his journey through science, and his thoughts on freedom in research and science. So I hope you enjoy the episode, and here we go. Today we have Professor Roland Bennewitz with us, who's the head of the Interactive Surfaces Research Department at the Leibniz-Institut for New Materials. So welcome, Roland.
Thank you for having me.
It's great to have you, and there's a lot I can tell about you, but we thought it'll be a bit more fun if we get to know you through the classic old game of three truths and a lie. We're basically going to tell me 4 statements, and I have to figure out which one is untrue.
Okay.
So, yeah, go ahead and keep my ears.
Yeah, okay. So they are, of course, research related. So as you all know, I'll tell you now, my research is about friction, so sliding surfaces in contact. So we study how friction actually works from a molecular level for materials, and we try to understand which materials have high friction, which have low friction, and so on. So my 4 statements are all about friction.
Okay.
First one, I have led several research projects where we measured friction out of contact. So we actually did not touch the surfaces and still measured friction.
Okay, so I guess I should have a chance to dig into these statements to kind of figure out if it's true or not. Is this AFM based?
Yeah, so also we did several, but it's mostly AFM. So we have a fine tip, and so we are moving the tip quickly in small oscillations over the surface. And we try to see if our instrument is sensitive enough to pick up any friction which is actually non-contact, which even gives lateral forces without being in contact for certain materials.
Okay, this sounds a bit voodoo-like, but let's go on to the next statement and see how that goes.
Well, we also explore fingertip friction on materials because we want to understand how people perceive materials by touch. And so one of our projects, we actually put a microphone here and we play back the sound of friction to the participant in order to change his perception of the material, his tactile perception of the material.
Okay.
So it's like, actually, we just play back a little bit, sort of, we have a nonlinear amplifier in there, so we make a little sound game from what they actually do with the finger, and we play it back and they feel different just by sound.
Oh, they feel it different just by sound. Okay. And do you learn something from the sound?
Like about perception. This is about cross-modal, because if you perceive a material, it's not just by touch, it's also by smell, by sound, by vision. And so we would like to learn more about the cross-modal sort of impressions, so about our different modes of perception.
Okay, so both touch and sound, how that influences
each other.
Yeah, okay. And
exactly.
I can kind of relate to this because I play virtual reality, and then the sound and the feeling in your
ears
These makes a big...
You will be our customer at the end.
Yeah, okay.
Exactly. Yeah,
that'll be perfect. Yeah.
Okay.
Okay. So, but that is what you said. You have done that with real volunteers. That's
absolutely. Yeah. As a scientific study. Yes.
Okay. As a scientific study.
Yeah. Okay. So number 3 is about nanoscience. So we are using a very, very fine tip to measure friction. It's actually so small, it touches only with 1 of 2 atoms, the surface.
Mm-hmm.
And this experiment is so small and so sensitive, and computing power is so big these days that we can do quantum mechanical calculations, which simulate exactly our experiment. So there's a perfect overlap between quantum chemical calculations of the situation, so modern physics applied to this piece of material science, and we have a perfect overlap of experiment and quantum mechanical calculations, only in the last few years though.
Only in the last few years. And you have developed these models?
We have done the experiments. No. These are done on supercomputing centers in Germany who have enough computing power. No chance with a normal computer.
Okay, so it takes into accounting all sorts of quantum weirdness and...
Well, no, not weirdness. Actually, just that the covalent bonds and how the energy from friction is coupled into the atomic system.
Okay. Everything with quantum can be true or false. Okay.
Both at the same time.
Yeah, actually, that's more true than...
Okay, number 4 is, so you know graphite, right? So this is layers of carbon. In one of our friction experiments, we pressed with our AFM tip so hard on the graphite that we accidentally made diamond under the tip.
Ooh. This sounds a little bit made up. Okay, wait, let's dig into that a little bit. Okay, is that even possible? Because graphite has a completely different lattice structure than diamond.
No, that's not true. It's very similar. The layers
it's just 3 layers.
It's just that in graphite, the chemical bonds are only in the layer, and in diamond, they're actually also between layers, the covalent.
Yeah, okay.
And usually diamond is done only in geological things. So you need a high pressure, high temperature. But with our very small tip, you can exceed this pressure and can actually make diamond very locally, only under the tip.
Okay. This sounds actually doable now.
Well, little diamond.
Okay.
So just to
so maybe one question on that. How did you know that it was a diamond?
Actually, well, that sort of we saw that there's suddenly when we exceed this pressure for making diamond, the friction goes up by a factor of 10 or 100. And this is a signature of this having made diamond and having made these extra covalent bonds.
Okay, so diamonds offer greater friction than graphite.
Yes, because graphite has no bonds off the surface, while diamond does have bonds off the surface.
Okay, and you made how big is this diamond we're talking about?
1 nanometer.
1 nanometer. Okay, so more than just
the tip.
Just one lattice of diamond. So it's
it's more like it's like 20 atoms being diamond.
20 atoms of diamond.
Yeah.
And is this scalable, you think?
No. I mean, of course. I mean, like in the earth, in the crust.
Yeah, okay. That's true. But in the lab, no. Okay.
In the lab, no. Artificial diamond is done. It's made in
okay. So my wife is not getting a special Christmas gift.
Not for me, no.
No. Okay. Can you recap the four statements?
So four statements on friction. So we have done scientific projects measuring friction without being actually in contact. We investigate the interaction of sound and of the sound of friction and the touch of friction in perception of materials. We are actually doing now experiments so small and so sensitive that they have perfect overlap with supercomputing of quantum mechanics of the same system, of the same size, on the same time scale. And number 4, we have actually made locally diamond by just pressing with a small tip of our instrument on graphite.
Okay, so for me, the first one, now I think I can correlate with it because I do know that you do atomic force microscopy in contactless mode. So that even I've been part of. Whether you can do friction with that, I don't know what that means actually, because everything I know about friction is, touching and...
Well, measure a force which resists sliding.
Okay. Yeah, okay. In that sense, I could relate to that. The second one sounds completely doable and sounds like the kind of thing that you do. The third and fourth are the most suspect. The third, because I don't know enough about quantum mechanics except that it's spooky.
Expensive.
Yeah. And the fourth one, I want it to be true. Let's say it's more like that. I feel like that might be the one over the top. No, I'm going to go with statement 3. The quantum mechanics. Yeah.
Oh, you got me.
Yeah, I got you. Oh.
We are a factor of 1 million between experiments and quantum mechanical calculations. You cannot possibly calculate more than 10 atoms in quantum mechanics, maybe more than 10, but not more than 100. And in particular, you can never do the time scale because heat, the frictional heating that we see, right? This is vibration of the lattice.
Okay.
The temperature is essentially nothing like atoms vibrating with respect to each other. And this is very, very slow on the time scale of quantum mechanics.
Okay.
And you would have to calculate for 10 to the 20 years to actually ever finish a calculation on that. So no chance, unfortunately, right now.
Wow. Okay.
So that's true. But we have this gap of at least 1 million in time scale between experiments and computing.
Yeah, that's fascinating. And I think quantum stuff is perfect for sneaking in a lie into your statements.
Well, a certain uncertainty. I mean, you need experts. You really good experts on the quantum mechanics itself is not difficult. It's actually a relatively simple concept. But doing the numerical calculations, doing the correct computing and the rounding errors in the right way, that is really something involved. Yeah, that's true.
So it's something that you can do on the scale of a single atom, or I don't know.
Yeah. You can calculate like the absorption states of an atom, or you can calculate even the bond between 3 atoms, no problem.
Okay.
You can even calculate the contact between our tip and the surface in static case, no problem.
Okay.
But doing the dynamics of friction, that doesn't work.
That doesn't work. Wow. Okay. Okay, that's good to know. It's good to know that no one's going to sneak that past me in the future also. I know the limits now. Cool. So these statements you're talking about, are these things, the 3 that were true, are these things that you've been doing at INM, at the Leibniz-Institut for New Materials?
Yes, mostly. I mean, the haptics experiments are all done here. So this is a bachelor thesis of Kim Yost. So she's currently working on the fingertip interaction with materials. And so now we bought this microphone and we're setting up the whole audio setup to sort of, essentially we want to trick participants into using a particular force when they touch the surface. Okay. And by playing it too loud when it's too high for our taste and playing it too weak, if it's too low the force, we try to trick them using a very definite force to touch our materials.
And does that work? Have you seen?
No, that's
upcoming. That's upcoming. Okay. Okay. What kind of materials do you have that people are going to touch?
So Kim started her project during Corona, and she actually needed a sample that could be made new for each participant.
Oh, yeah.
So she went for wrapping paper, gift wrapping paper. She wanted to understand if people can feel the value of gift wrapping paper.
Okay.
And so we are working in collaboration with psychologists. So they said we should be action-oriented. So the question she asked is, which paper would you use to highlight the material value of your gift? And it turns out that unfortunately our participants went for the cheapest Karstadt department store paper, the happy birthday paper.
Okay, but this is by touch and sound only?
Only by touch.
Without looking at it?
Yeah. Actually, in her first study, even without sound, we put big headphones on their head and just...
it was in an empty box and then you... And they pay you to do this? Yeah.
No, that was actually
It sounds fascinating. Okay. No, it's very interesting work.
And the diamond, this is actually the PhD thesis of Bartosz Stefanovic, who's just finished and who's defending this. So if you want to know more about diamonds under the tip, there will be his defense before end of the year.
Oh, that sounds interesting. Nice.
And
but was that a purpose for him? Like
we suspected that, and in his thesis he worked hard on actually making this reproducible.
Okay.
The problem is that the little tip also starts changing its character when under this very high pressure.
Okay.
And all this has to be done in a very, very clean atmosphere. So in the basement here we have a machine where the pressure is practically 0 and everything is perfectly clean.
Okay.
And that's what he has been doing experimentally. And the non-contact, that's an older project, which I brought actually here also, but we are still doing. Yeah.
So, and that one is basically whatever forces this tip is feeling against.
The question is essentially if the tip is moving a charge in the surface when it's not in contact, but it sees the mirror charge in the sample and it's moving the charge back and forth. But it only works if we go very, very fast.
Oh, if we go how fast?
How fast? So we are oscillating the tip with 250 kilohertz.
250 kilohertz.
Over 10 nanometers. So it's still sort of slow on
a quantum scale.
Yeah. Well, this is a big problem. I mean, all our experiments in friction are usually a little bit too slow. Like we are also now working on the friction between hydrogels, like between our eye and our eyelid. but our eyelid is incredibly fast. It's meters per second, and it's really difficult in the experiment to measure meter per second.
Yeah, okay.
But so many applications are a little faster than we can do.
Yeah, okay. Maybe we got to find the person with the slowest blink.
Eyelid blink,
Like,
yeah.
and try to simulate that. No, but yeah, that is incredibly interesting. So all of this is what you're doing now, or what you've been doing at the Leibniz-Institut for New Materials. And before that, from what I know, you were in Canada,
Right,
I guess, right? Yeah. So what led up to the work you're doing now on friction?
Yeah, so in Canada, I was in the physics department, not in the Material Science Institute. So our work in Canada was really even more fundamental. So we were mostly looking at atomic friction. So we are trying to measure really how surfaces move atom by atom with respect to each other. So there's something called stick and slip. So we really see, and actually can also hear if we want, the force is doing something like
Oh, okay.
and so we're trying to understand from a molecular level how sort of the unbinding and rebinding between the materials is proceeding.
But are you touching there, or are you?
Yeah, we are touching.
Okay,
Yeah.
touching.
And so we started also in Canada to do this not only in vacuum, but we did it also in electrochemical cells on a liquid-solid interface. And we tried to switch friction by changing the electrochemical potential between tip and surface.
Okay.
And so these were things we were doing there.
And these are for batteries, if you're talking about electrochemicals?
No, actually, we were more interested in understanding if we can actually find a way of switching nanomachines. Like if we have very small microelectromechanical systems, if we can actually switch on and off friction in the system.
Okay.
It's really hard.
Switch on and off friction.
Yeah, that was essentially the idea.
Okay.
Yeah, and yeah, in vacuum it's quite difficult, but in electrochemical cell it's quite possible.
And you can switch friction.
Yeah. The only problem is that electrochemical surfaces are notoriously ageable. So you have some very nice electrodes like gold or platinum. They work well, and we were quite successful on those. But if you want to go to a more cheaper material, it's not so.
Okay.
So some people claim that gold is not a material; it's simply too expensive.
Yeah. Okay. So what is it that's actually changing the friction there? Like, is it the atoms rearranging themselves, or?
Yeah. It's essentially that you can switch between a perfect gold surface and a gold surface that actually has chlorine ions attached to every second gold atom, and that simply has a higher, if you wish, atomic roughness.
And would this be perceivable by hand for us?
Except that you cannot use your finger as an electrode, yes.
Okay.
Okay, yeah.
Okay, yeah. Well, that's really good to know. And so then you moved from Canada to Saarbrücken, all the way to Germany, back here. How was that transition?
That was, first of all, it's actually making life much easier if you do not live in Canadian winter.
Okay.
So, I saw actually the new director taking over INM, Professor Arts at the time.
Mm-hmm.
He had an opening saying, "Oh, we are looking for this field to be established at our institute," and one of the fields was nanotribology.
Okay.
And I was doing that, and it was a very, very sort of well-established field of research in the United States and Canada, but it was actually practically never explicitly mentioned in Germany.
Okay.
So he was one of the first people who actually actively looked for doing that. And so I was fascinated. I didn't really know him, but so we got in contact, and I asked, and it was a very good opportunity. So it was no question to return here, and to also the spin of going more towards materials physics was very attractive for me.
Oh, nice. Yeah, and then now you've gone into something that's actually, with the whole touch sensation, is very application oriented.
Yeah, and also even in between. I mean, this graphene is actually, we still have some hope that is also something that is quite relevant for larger scale.
Mm-hmm.
I don't know, I can show.
Yeah, talking about graphene, so you brought here materials with
one
you.
of my favorite materials. So let me say a few words about graphene, if you don't mind.
Okay, yeah.
So
go ahead.
Graphene is one layer of carbon atoms.
Mm-hmm.
Chemical bonds in the plane, no bonds off. In 1954, funny enough, at McGill University, where I was professor in Canada, a theoretician, a physicist, calculated that the mobility of electrons in graphene should be infinite. A very, very theoretical work. And people said, sure, why not? Yeah?
Okay.
But there is no graphene. No one was able to make graphene, one single layer of atoms. And so people said, sure, why not? Then, much, much later, in the 90s and early 2000s, Andrew Geim and his colleague Novoselov, they actually found a method to produce one single layer of graphene, famously by actually Scotch tape.
Yeah.
They simply divided graphite so often until they got it. But they knew, this was, of course, ingenious, but what they knew very well is how to make contacts and how to measure electronic properties of these very small systems.
Okay.
And they confirmed that this is actually very high mobility. And so then, after this, people discovered there's many ways of producing graphene. And one of the ways is actually to taking silicon carbide, which is made of silicon atoms and carbon atoms. And if you heat silicon carbides in the oven to very high temperature, you start evaporating the silicon, but not the carbon. And so at the end, you have one layer of carbon on the surface. So you can actually use silicon carbide, just heat it under the right conditions, and you get one layer of graphene on top of the silicon carbide. And so I used that. I could show in one of my probably most best-known works from Canada that the friction is super low on this one layer of graphene on silicon carbide. So this was sort of well-received scientific work. Then I moved here. And when I arrived, I said, blah, blah, I'm doing this, and I'm doing graphene on silicon carbide. And one of the old people of INM, who have been here for a long time, came to me and said, oh yeah, I can do that. I said, how so? He said, we have had a ceramics group for a long time in INM. And this is actually silicon carbide ceramics made by this INM patented method. And he said, we can actually also polish this, put it in the oven, and produce one layer of graphene on our silicon carbide ceramics. And it worked, actually. So we could prove that there's one layer of carbon atoms on this, and we could show that the friction is extremely low. So it was really nice to see that it took from 1950 till 2000 to actually realize that graphene is not just a theory, but it's actually an interesting material. And then it turned out that there's many ways of making graphene, and one was actually established at INM by chance. So
for those who are listening only, maybe you can describe exactly what...
Yeah, so what I have here is 1 inch, so 2.54 centimeter disc in my hand, which is grayish. It has significant weight, silicon carbide, and it has a polished surface, and I can actually see my host in the mirror here.
Yeah, it's reflective.
And so that looks almost metallic, and yeah, it has this shiny graphene surface, which at least was there a few years ago when we studied it.
Okay,
we would have to check again. So there's a method established here in the institute which is called Raman spectroscopy, which looks into optical properties and which can identify graphene to the one atom.
Okay, wow. Can I have?
Absolutely, sure.
Okay, so yeah, it is reflective as you see it. And can I touch it on top?
Yeah.
It probably doesn't have graphene anymore.
Oh, it may have, but you can still.
There's no problem in getting graphene on my arm, right?
At the end, we will have graphene plus something else.
Yeah, okay.
It's actually fun because it turned out that people found out that iridium, which is a metal, is a very good catalyst for graphene. So if you have carbon materials on iridium and they heat it in vacuum, you get graphene. And one of the colleagues here at university, he showed that you can use any carbon materials. So he started with butter.
Yeah.
And he showed that with butter, you can make graphene on iridium. And at the very end, he cleaned the iridium and he just put his fingerprint on top and put it in the oven, and he got graphene also.
Wow.
So all you need is carbon source and iridium and a lot of heat, and then you can...
And then you get graphene.
Yeah. So it's a quite interesting material in that there's now many pathways to making it.
That's really cool. Yeah, I've always wondered about how much Scotch tape is being used in the industry to get us our graphene.
None, of course.
Yeah.
And we don't really know what the big industries are doing now. We know that companies in Korea are able to cover a full screen, like a big TV screen with graphene as an electrode, as a transparent electrode. But we are not sure how they actually do it. But
is it a single layer?
Yeah, so one layer of graphene,
So
it's
TV screen.
Yeah. So they can do it. We don't know. Maybe some of our colleagues who travel to Korea a lot know it, but I don't know it.
Wow. Okay, and what is the why? Is it for touchscreens?
I think it's just, for all these new screens, you need a transparent electrode, right? You have to apply a voltage in order to switch the pixels, but you have to go, see through it. And the classical material, which is also done here at INM, is ITO, indium tin oxide.
Yeah, okay.
But graphene was, for a long time, considered to be probably the better material.
Yeah, okay. And is your research moving along with graphene?
I have a few ideas still. I think that a lot of things are done now, and we have a good feeling for what is going well with frictional graphene, what is good in lubrication. But if it comes to real devices, I think the only application that's currently really being discussed is micromechanical systems, so little cantilevers micron size which touch, or for example, if you in your beamer, right? In your beamer, there are little mirrors which are switching forth and back, and they usually have an adhesion problem. So currently, it's being lubricated with an alcohol vapor.
Okay.
If that could be replaced by graphene, that would be actually simplify the production process quite a bit. And things like that are being pursued, but that's not what we are doing, right? I mean, we're not doing any engineering of these structures. So
okay. Is there a sense to coat people in graphene for wearables or something like that?
No, I don't think I've seen that. But what we have done in the institute here, and the colleague, one of our colleagues has actually put a living cell into a droplet of water, essentially, and put graphene on top, and then put the whole cell into vacuum. And he could show that the cell will actually survive, although it's in vacuum, because the graphene is actually waterproof. It's only one atomic layer, but it's waterproof. Okay. So you can actually keep the liquid in the cell. And then he was using his electron microscope to look at the living cell, biological cell, by shooting through the graphene and through the cell. And when you ask him, is the cell still alive? He says initially yes.
Okay.
So that is a quite fascinating method, applying graphene. And so one of my ideas for maybe also our collaboration in the future is to cover hydrogels with graphene to keep them wet.
I'd love that. Yeah. Right now we use silicone oil and so on. It's a pain to
easier.
work with. Okay. There is a common theme sort of that I noticed, like with you coming from Canada here to INM, where you said, no one is doing tribology or nanotribology, and INM wanted to look into this new field. There's a similar arc for me where I'm doing engineered living materials, so incorporating bacteria in materials, and no one was doing that in Germany. In Germany. And at INM we got to explore this new thing, and now it's actually kind of pervaded into Germany much more. So it is kind of an interesting hub in the corner of Germany, Saarbrücken here, the institute, where we get to explore these new funky ideas.
And it's and where you have the opportunity to collaborate between people. I mean, this is sort of the idea of INM, right? For me, that we have different groups from different disciplines that actually collaborate, and so in this atmosphere, you may sometimes be not as deep into one topic as if you have, for example, in Heidelberg, in the physics department, you probably have 64 people working in astrophysics of distant galaxies or so. So they may reach a certain critical mass, which goes super deep. That's one concept of science, right? And the other concept, which I think is more appropriate to material science, is to sort of rather have a combination of people from chemistry, physics, and material science, and now biology that work together in defining the actual projects.
Yeah, and that actually gives me a nice segue into the last part of what I want to ask you. So our Federal Ministry for Education and Research, the BMBF, they've declared this year's Year of Science topic as freedom.
Yes,
which is, I think,
about that.
Along the lines of what we've been talking about a little bit. Like, so what does freedom in education and research mean to you?
Yeah, that's an interesting point, because in Germany, as you probably know, the freedom of research is actually a constitutional guarantee.
Okay.
So our constitution says the freedom of research is granted. which is very unusual. I mean, different countries have different constitutional rights. And for example, in Canada, just to mention something, retirement is unconstitutional.
Oh,
No company can retire someone just because of age. It's considered age discrimination.
okay.
So you cannot force someone to retire. And here in Germany, it's the freedom of research. And the interesting part is that scientists in Germany consider this an individual right to pursue the projects they want with the methods they want. And the question, of course, is what are the limits?
Yeah.
How many people can we finance who do what they want and what they consider good? And also, what are the limits for example, I mean, the obvious problem is always genetically modified organisms. Where are the limits in freedom of research here? In Germany, we have certain limits. In other countries, we have less strict limits. In even other countries, we have more strict limits. So there's anyways the limits. And I always find that scientists in Germany who put a very strong emphasis on this individual right to do what they want, they're a little bit out of proportion to the societal role of research. So I think they should better, I think we should all think about what society really needs and what our role is and how we are organized, because freedom of research sometimes seems to indicate that the individual is a genius who knows by him or herself what research really is. And I rather believe that science is it's sort of an agreement of procedures within a society and a sub-society, let's say, and we should be aware of that. And that is that's one aspect. And I don't know, can I add a second one?
Absolutely, yeah.
There's no freedom without peace. So I've grown up in peace.
Yeah.
I've not experienced violence in all my life, which is exceptional in our history. And that is something that I miss sometimes in the discussion of freedom, that we are now discussing in two wars that we are actually sort of considering all day. What is freedom? What is peace? What's the value of freedom versus peace? And our freedom of research is granted only by peace. So we should be very, very, very aware of this and work hard to maintain peace in our institutions, in our society, between our nations. So that is for me the other limit on this freedom thing. We'll see how the science here will evolve and how this will be discussed. I'm actually very interested. We had the science here of light.
Yeah.
And we had a very interesting series of discussions about light.
Okay.
We had one on randomness.
Okay.
And that was very interesting.
It sounds very freedom.
Yeah. No, it was actually mostly about, it was actually the German word Zufall.
By chance?
By chance, also, right? So there were actually also talks by a genetic researcher. There were mathematicians. So and so now for freedom, we will probably have politicians. We have maybe philosophers. But I hope also that we will have sociologists.
Yeah.
I believe they have the most to say, as I tried to explain.
Yeah, I mean it's a deep subject, and it's definitely something worth the freedom to research into. And as you said, with peace, this is something I experience here. In general, we have a pretty good level of peace at the Institute, and so we get to explore, we get to use each other's devices and so on. And other places, those things cause restrictions when you don't have that peace.
And one part of freedom and peace is, of course, what we call often now diversity, which I experience as also very positive here at the Institute. We are very, I mean, even if you don't think about international colleagues or even among the people who are from Saarland, for example, they're a very diverse group also, and they can be very diverse scientists here. So, and that's very important for me too.
Yeah, absolutely. So on that note, I think let's end the podcast.
Okay.
It was wonderful talking with you.
Thank you, and for the interesting discussion.
Yeah, you too. And let's do this again sometime.
We will. Okay. Bye-bye.
Bye.